your region had better be rectangular. Okay? And the reason for that is, if we think about what we said here, let's say I want to set up this integral, and this one we'll do both ways. So here I'm going to do this one in terms of y and then x, and then I'm going to do it again in terms of x and then y. And like I said, this is the only one I'm going to do both ways, because with the rectangular regions, these are really nice. They have some great properties, and one of those really nice properties is the fact that all of my limits are constant. Okay? So in this example here, if I'm doing y first and then x, again what it says is when I'm looking at the y, I want to think of a vertical line being drawn through the y, and I want to figure out where it starts and where it stops. And again, the key word in that sentence was any. The one I've drawn is not the only one I want to look at. I want to think of moving that line throughout the region and figuring out every place it starts and find that lowest value, and every place it stops and find that highest value. And you can see with the rectangular region, the nice thing is, it doesn't matter where that line is, it's always going to start at y equals 0, and it's always going to end at y equals 3. So my limits here are going to be 0 to 3. Okay? And then for my outer limits, because my outer limits are x, again I can think of mentally squishing this down to the x-axis and figuring out what that imprint looks like. And here again we can see nicely, if I squish that down, I'm basically just going to get a region or an interval from 1 to 4. Okay. Now if we reverse the limits of integration, again on a rectangular region, I'm going to do just the same thing but the other direction. So here, because my x's are first, I'm going to draw a horizontal line, and I want to find where it starts and stops. And again, I can think of moving that horizontal line up or down and figuring out for any place on that region where it starts and stops. And here we can see, no matter where I move that line, it's always going to start at 1 and it's always going to stop at 4. And likewise, when I look at the y's, if I squish that over to the y-axis, we can see that it's always going to start at 0 and end at 3. And this is why I said it doesn't matter which way I do it for a rectangular region. We can see that the x values are always going to be 1 to 4, and the y values are always going to be 0 to 3. And this is the nice thing about those constant limits. Now again, once my region becomes non-rectangular, this doesn't work. Okay? So let's look at region 2 that I have here. So region 2 is another nice geometric figure. This is our triangle. And so in this case, again, I want to start by figuring out which way I'm going to integrate. And to do that, I'm going to start by figuring out what my equations for these lines are. Okay? And so the first thing I notice is that this line here is just the line x equals 4. This line here I can find using my y equals mx plus b. So to find this line, again I can think y equals mx plus b, and I can see my slope here is basically, so in this case I'm going up 1 and over 1, and my intercept is going to be down there at negative 1. So my y is going to equal x positive x minus 1. And we can double check that. For example, if I plug in 3, I see I'm going to get a value of 2. If I plug in 4, I get a value of 3, and so forth. So there's my equation of my lines. Okay? And so here, if I'm thinking about what we did for the rectangular region, I can think, well, if I do a vertical line drawn through my region, I can see that depending on where it is, the start value is always the same, but the end value is going to change, right? In this picture, as I've drawn it, my end value is here, but if I drew my line over here, my end value is down here. So it's no longer just a constant value. And so here we can see that if I do my integral in terms of y and then x, then I can see that the start value for my y's is always 0, but the end value is basically that line, meaning y equals x minus 1. For the x's, again, once I've done that, I'm going to squish it down to the x-axis, and I can see the imprint is basically going to be from 1 to 4. Okay. Now, just for this one, again, I'll go ahead and do the other direction. So, if I'm looking in the other direction, and do x first and then y, then I can see with my horizontal line, the end value is the same in all of them. The end value is going to be that 4, but the start value is going to change. So again, if I start on this line, it's going to be there, but up here if I start, it's going to be that point there. Okay? And so again, I can see that this line is my starting value, but now I need it as an x equals in terms of y. So here, I'm just going to rewrite my equation, and I can see that x is going to equal y plus 1. Now, for my y limits, again, I'm going to squish this over to the y-axis, and I can see that the imprint there is going to be 0 to 3. Okay? And so, again, if it's not a rectangular region, we can see that the limits don't just change. They do a little bit, but the functions for those limits really does make a difference. And the other thing to notice is they're no longer constant for all the limits. I'm now going to have some variable limits in my integration. Okay. All right, so let's look at this next region. This is region 3. All right, so now for this one, this is where I actually do want to determine my limits of integration, which order I'm going to do it in. So here, if I look at this, there's kind of a nice one and a not so nice one. And again, the way I'm going to determine this is by looking at vertical lines versus horizontal lines. Okay? And here I can see that if I try to integrate with that blue line first, then I have a problem in that the start and the stop are exactly the same curve. Okay? So here, I cannot integrate dx dy. Because if I try to do the x's first, my upper and lower curve are going to be the same, and they're basically going to cancel out. I'm going to get an area of 0. Okay? So here, I'm going to do my integral as a dy dx. Okay? Which means looking at this kind of purplish line, I want to figure out where this is going to start and where it's going to stop. And again, no matter where I move that, I can see it's going to start on the x-axis, so at y equals 0, and it's going to end along the curve. And the curve, we have the equation there, it's the square root of 1 minus x minus 2 squared. Okay? Not a pretty limit, but it works. Okay? Squishing that down to the x-axis, I can see that the imprint is basically going to be that interval there. So the interval from 1 to 3. Okay. Now, if I look at region 4, okay, same thing, I want to figure out which way I want to integrate first. So again, I'm going to draw a vertical line there, and I'm going to draw a horizontal line. Okay? And one of the things you'll notice here is, even though this one's not rectangular or a nice geometric figure, this one, it doesn't matter which way I go. I don't have the problem that it's the same curve top and bottom or left or right. So here I can actually set up two different integrals. Okay? So again, if I want to do the dy dx, we can see where it starts and stops. No matter where I move on that curve, the start curve is going to be the x cubed, and then the top curve is going to be that x squared. Squishing that down to the x-axis, we'll see that my imprint is basically going to be the integral from 0 to 1. Okay. If I go the other direction, so if I integrate dx dy, then same thing, if I start with the x's, I can see that my first curve that I'm going to hit, so going in this direction, is going to be this curve. But again, it's x equals. So here I'm going to have to rewrite this as x equaling the square root of y. And I don't want the plus or minus one there because I'm only looking at the positive side of this. So square root of y is where it's going to start. And then I can do the same thing. As I move along the curve, no matter where I am horizontally, it's always going to end at y equals x cubed, which again I'm going to need to write as x equals the cubed root of y. Okay. Again, squishing that to the y-axis, I can see that the imprint, if I do that, is going to be from 0 to 1. So there's some different examples of regions and being able to set up the integration for those. Once we have the integration set up, again, it just goes back to evaluating those and being able to solve. So just like with the area, your volume is going to work very similarly. And so now I'm going to do an example that puts everything we just talked about all together. Okay, so here we have a region described for us. And we want to find the area and the volume of f of xy equaling e to the x plus y over this particular region. Okay. Now, one thing to keep in mind, this is really two separate problems. For the area, remember we don't actually need the function, we just need the region. And then for the volume, we need both. Okay. And so here, again, the first thing I'm going to do in this type of a problem is I'm going to start by figuring out again what my equations are and figure out which order of integration I want to do. Okay? So here, let's start by finding our equations. So nicely, if we look at this, we can see for this line over here, the slope is just 1, and the y-intercept is 1. So this line here is just y equals x plus, I said that wrong. The slope is negative 1, and the y-intercept is 1. So y is going to equal a negative x plus 1. And then over here we can see the slope is positive 1, so rise over run, and the y-intercept is 1. So this one is going to be y equals x plus 1. And again, we can check those. At negative 1 we get 0, at 0 we get 1. Here at positive 1 we get 0, at 0 we get positive 1. Okay. And of course, this line down here, this is just y equals 0. Okay. So again, the first thing I want to do is figure out which order I'm going to integrate. So again, I want to look at vertical lines versus horizontal lines. And the first thing that should be very apparent is if I try to do a vertical line, the problem is my upper curve is going to change depending on which side of the y-axis I'm on. So here, I really do want to integrate this direction first and then worry about integrating the other direction. Okay? So here in my integrals, I'm going to want it so that x is first and then y. And if I look at my limits on x, they're going to start over here at the y equals x plus 1. Again, I need it as an x equals, so that's going to be a y minus 1. And it's going to stop over here at y equals negative x plus 1. Again, putting it in terms of x, says x is going to equal negative y plus 1. Okay? From there, I'm going to squish this to the y-axis to figure out what my limits in y are. So squishing that, and I can see that my imprint is going to be from 0 to 1. Okay? So there's kind of the setup for my integration. Now let's actually set up our integrals and solve them. Okay? For the first part, my area, well, we've basically already set it up. Okay? Again, we don't need our function in there, so the integral from 0 to 1, integral from y minus 1 to negative y plus 1, dx dy, that'll give me my area. Okay? So I'm going to integrate the inner piece first. So integral of dx is just x, and I'm going to integrate that from y minus 1 to negative y plus 1 dy. So my upper limit minus my lower limit is negative y plus 1 minus y minus 1. Again, I can clean that up before I integrate again. So minus y looks like a negative 2y. The 1 plus 1 looks like 2. So there's my one variable integral. Okay. From there, integrating with respect to y, we'll get a negative y squared plus 2y, integrating from 0 to 1. At my upper limit, I can plug in. I'm going to get a negative 1 plus 2. At my lower limit, we can see that's going to go away. We'll just get 0 and 0. So my area here is just going to be 1. And again, we can check this. Nicely, this is a nice geometric region. So we know that area is base times height. 1/2 base times height. So my height, we know, is going to be 1. My base is from negative 1 to 1, so that's 2. And 1/2 of that, we can see, is going to just be 1. Okay, so we know we did that right. Okay, so let's look at the volume. Now again, what the volume is saying is I've got this function e to the x plus y up here in the z-plane, and it's being imprinted over this region. And so we're thinking of the distance between that function and the region is the height times that area. So that'll give us our volume. So here, our volume, again, the difference between these two formulas is now I'm going to plug in my function. So same limits we just had. I'm going to put an e to the x plus y in here, integrating dx and then dy. Okay. So integrating in that innermost interval first, I'm going to integrate with respect to x. So the 0 to 1 just gets carried down. Antiderivative of e to the x plus y. Well, that's just e to the x plus y. Okay. Again, if you don't see that right away, let u equal x plus y. Our du is just going to be dx. So again, we're not going to divide out by anything. We're going to evaluate this from y minus 1 to negative y plus 1. So plugging in at our upper limit, we're going to get an e to the minus y plus 1 plus y, minus, at the lower limit, e to the y minus 1 plus y. So remember, you're plugging in for x there. Okay. Again, we can simplify. So 0 to 1, simplifying here, the y's cancel, so we're just looking at e to the 1 minus over here, e to the 2y minus 1. Okay. Now we're going to integrate. Now here you got to be a little careful, this one's kind of tricky. E to the 1 is just a constant, so when we integrate that, we're going to get y times e.